Clock rate. From the main article, clock rate. Most CPUs, and indeed most sequential logic devices, are synchronous in nature. That is, they are designed and operate on assumptions about a synchronization signal. This signal, known as a clock signal, usually takes the form of a periodic square wave. By calculating the maximum time that electrical signals can move in various branches of a CPU's many circuits, the designers can select an appropriate period for the clock signal. This period must be longer than the amount of time it takes for a signal to move or propagate in the worst-case scenario. In setting the clock period to a value well above the worst-case propagation delay, it is possible to design an entire CPU and the way it moves data around the edges of a rising and falling clock signal. This has the advantage of simplifying the CPU significantly, both from a design perspective and a component count perspective. However, it also carries the disadvantage that the entire CPU must wait on its slowest elements, even though some portions of it are much faster. This limitation has largely been compensated for by various methods of increasing CPU parallelism. Architectural improvements alone do not solve all of the drawbacks of globally synchronous CPUs, however. For example, a clock signal is subject to the delays of any other electrical signal. Higher clock rates in increasingly complex CPUs make it more difficult to keep the clock signal in phase, or synchronized, throughout the entire unit. This has led many modern CPUs to require multiple identical clock signals to be provided in order to avoid delaying a single signal significantly enough to cause the CPU to malfunction. Another major issue as clock rates increase dramatically is the amount of heat that is dissipated by the CPU. The constantly changing clock causes many components to switch regardless of whether they are being used at the time. In general, a component that is switching uses more energy than an element in a static state. Therefore, as clock rate increases, so does heat dissipation, causing the CPU to require more effective cooling solutions. One method of dealing with the switching of unneeded components is called clock gating, which involves turning off the clock signal to unneeded components, effectively disabling them. However, this is often regarded as difficult to implement, and therefore does not see common usage outside of very low-power designs. Another method of addressing some of the problems with a global clock signal is the removal of the clock signal altogether. While removing the global clock signal makes the design process considerably more complex in many ways, asynchronous or clockless designs carry marked advantages in power consumption and heat dissipation in comparison with similar synchronous designs. While somewhat uncommon, entire CPUs have been built without utilizing a global clock signal. Two notable examples of this are the ARM-compliant AMULET, AMULET, and the MIPS R3000 compatible mini-MIPS. Rather than totally removing the clock signal, some CPU designs allow certain portions of the device to be asynchronous, such as using asynchronous ALUs in conjunction with superscalar pipelining to achieve some arithmetic performance gains. While it is not altogether clear whether totally asynchronous designs can perform at a comparable or better level than their synchronous counterparts, it is evident that they do at least excel in simpler math operations. This, combined with their excellent power consumption and heat dissipation properties, makes them very suitable for embedded computers. Parallelism. From the main article, Parallel Computing. The description of the basic operation of a CPU offered in the previous section describes the simplest form that a CPU can take. This type of CPU, usually referred to as subscalar, operates on and executes one instruction on one or two pieces of data at a time. This process gives rise to an inherent inefficiency in subscalar CPUs. Since only one instruction is executed at a time, the entire CPU must wait for that instruction to complete before proceeding to the next instruction. As a result, the subscalar CPU gets, quote, hung up, unquote, on instructions which take more than one clock cycle to complete execution. Even adding a second execution unit does not improve performance much. Rather than one pathway being hung up, now two pathways are hung up and the number of unused transistors is increased. This design, wherein the CPU's execution resources can operate on only one instruction at a time, can only possibly reach scalar performance, that is, one instruction per clock. However, the performance is nearly always subscalar, that is, less than one instruction per cycle. Attempts to achieve scalar and better performance have resulted in a variety of design methodologies that cause the CPU to behave less linearly and more parallel. When referring to parallelism in CPUs, two terms are generally used to classify these design techniques. Instruction-level parallelism, or ILP, seeks to increase the rate at which instructions are executed within a CPU. That is, to increase the utilization of on-die execution resources. And thread-level parallelism, TLP, proposes to increase the number of threads, that is, effectively individual programs, that a CPU can execute simultaneously. Each methodology differs both in the ways in which they are implemented as well as the relative effectiveness they afford in increasing the CPU's performance for an application. ILP, Instruction Pipelining and Superscalar Architecture, from the main articles Instruction Pipelining and Superscalar. One of the simplest methods used to accomplish increased parallelism is to begin the first steps of instruction fetching and decoding before the prior instruction finishes executing. This is the simplest form of a technique known as instruction pipelining, and is utilized in almost all modern general-purpose CPUs. Pipelining allows more than one instruction to be executed at any given time, by breaking down the execution pathway into discrete stages. This separation can be compared to an assembly line, in which an instruction is made more complete at each stage until it exits the execution pipeline and is retired. Pipelining does, however, introduce the possibility for a situation where the result of the previous operation is needed to complete the next operation, a condition often termed data dependency conflict. To cope with this, additional care must be taken to check for these sorts of conditions and delay a portion of the instruction pipeline if this occurs. Naturally, accomplishing this requires additional circuitry, so pipelined processors are more complex than subscalar ones, though not very significantly so. A pipelined processor can become very nearly scalar, inhibited only by pipeline stalls, or an instruction spending more than one clock cycle in a stage. Further improvement upon the idea of instruction pipelining led to the development of a method that decreases the idle time of CPU components even further. Designs that are said to be superscalar include a long instruction pipeline and multiple identical execution units. In a superscalar pipeline, multiple instructions are read and passed to a dispatcher, which decides whether or not the instructions can be executed in parallel or simultaneously. If so, they are dispatched to available execution units, resulting in the ability for several instructions to be executed simultaneously. In general, the more instructions a superscalar CPU is able to dispatch simultaneously to waiting execution units, the more instructions will be completed in a given cycle. Most of the difficulty in the design of a superscalar CPU architecture lies in creating an effective dispatcher. The dispatcher needs to be able to quickly and correctly determine whether instructions can be executed in parallel, as well as dispatch them in such a way as to keep as many execution units busy as possible. This requires that the instruction pipeline is filled as often as possible and gives rise to the need in superscalar architectures for significant amounts of CPU cache. It also makes hazard-avoiding techniques like branch prediction, speculative execution, and out-of-order execution crucial to maintaining high levels of performance. By attempting to predict which branch, or path, a conditional instruction will take, the CPU can minimize the number of times that the entire pipeline must wait until a conditional instruction is completed. Speculative execution often provides modest performance increases by executing portions of code that may or may not be needed after a conditional operation completes. Out-of-order execution somewhat rearranges the order in which the instructions are executed to reduce delays due to data dependencies. In the case where a portion of the CPU is superscalar and a part is not, the part which is not suffers a performance penalty due to scheduling stalls. The original Intel Pentium P5 had two superscalar ALUs, which could accept one instruction per clock each, but its FPU could not accept one instruction per clock. Thus, the P5 was integer superscalar, but not floating point superscalar. Intel's successor to the Pentium architecture, P6, added superscalar capabilities to its floating point features, and therefore afforded a significant increase in floating point instruction performance. Both simple pipelining and superscalar design increase a CPU's ILP by allowing a single processor to complete execution of instructions at rates surpassing one instruction per cycle, IPC. Most modern CPU designs are at least somewhat superscalar, and nearly all general-purpose CPUs designed in the last decade are superscalar. In later years, some of the emphasis in designing high ILP computers has been moved out of the CPU's hardware and into its software interface, or ISA. The strategy of the Very Long Instruction Word, or VLIW, causes some ILP to become implied directly by the software, reducing the amount of work the CPU must perform to boost ILP and thereby reducing the design's complexity. TLP, Simultaneous Thread Execution. Another strategy commonly used to increase the parallelism of CPUs is to include the ability to run multiple threads, or programs, at the same time. In general, high TLP CPUs have been in use much longer than high ILP ones. Many of the designs pioneered by Cray during the late 1970s and 1980s concentrated on TLP as their primary method of enabling enormous, for the time, computing capability. In fact, TLP in the form of multiple thread execution improvements has been in use since as early as the 1950s. In the context of single processor design, the two main methodologies used to accomplish TLP are chip-level multiprocessing, or CMP, and simultaneous multithreading, or SMT. On a higher level, it is very common to build computers with multiple totally independent CPUs in arrangements like symmetric multiprocessing, or SMP, and non-uniform memory access, or NUMA. While using very different means, all these techniques accomplish the same goal, increasing the number of threads that a CPU can run in parallel. The CMP and SMP methods of parallelism are similar to one another and the most straightforward. These involve little more conceptually than the utilization of two or more complete and independent CPUs. In the case of CMP, multiple processor cores are included in the same package, sometimes on the very same integrated circuit. SMP, on the other hand, includes multiple independent packages. NUMA is somewhat similar to SMP, but uses a non-uniform memory access model. This is important for computers with many CPUs, because each processor's access time to memory is quickly exhausted with SMP's shared memory model, resulting in significant delays due to CPU waiting for memory. Therefore, NUMA is considered a much more scalable model, successfully allowing many more CPUs to be used in one computer than SMP can feasibly support. SMT differs somewhat from other TLP improvements in that it attempts to duplicate as few portions of the CPU as possible. While considered a TLP strategy, its implementation actually more resembles superscalar design, and indeed is often used in superscalar microprocessors, such as IBM's Power 5. Rather than duplicating the entire CPU, SMT designs only duplicate parts needed for instruction fetching, decoding, and dispatch, as well as things like general-purpose registers. This allows an SMT CPU to keep its execution units busy more often by providing them instructions from two different software threads. Again, this is very similar to the ILP superscalar method, but simultaneously executes instructions from multiple threads, rather than executing multiple instructions from the same thread concurrently. Vector processors and SIMD, from the main articles Vector Processor and SIMD. Less common but increasingly important paradigms of CPUs, and indeed computing in general, deals with vectors. The processors discussed earlier are all referred to as some type of scalar device. As the name implies, vector processors deal with multiple pieces of data in the context of one instruction. This contrasts with scalar processors, which deal with one piece of data for every instruction. These two schemes of dealing with data are generally referred to as SISD, or single instruction, single data, and SIMD, single instruction, multiple data, respectively. The great utility in creating CPUs that deal with vectors of data lies in optimizing tasks that tend to require the same operation, for example, a sum or a dot product, to be performed on a large set of data. Some classic examples of these types of tasks are multimedia applications, image, video, sound, as well as many types of scientific and engineering tasks. Whereas a scalar CPU must complete the entire process of fetching, decoding, and executing each instruction and value in a set of data, a vector CPU can perform a single operation on a comparably large set of data with one instruction. Of course, this is only possible when the application tends to require many steps, which apply one operation to a large set of data. Most early vector CPUs, such as the Cray 1, were associated almost exclusively with scientific research and cryptography applications. However, as multimedia has largely shifted to digital media, the need for some form of SIMD in general-purpose CPUs has become significant. Shortly after floating-point execution units started to become commonplace to include in general-purpose processors, specifications for and implementations of SIMD execution units also began to appear for general-purpose CPUs. Some of these early SIMD specifications, like Intel's MMX, were integer only. This proved to be a significant impediment for some software developers, since many of the applications that benefit from SIMD primarily deal with floating-point numbers. Progressively, these early designs were refined and remade into some of the common modern SIMD specifications, which are usually associated with one ISA. Some notable modern examples are Intel's SSE and the PowerPC-related Ultivec, also known as VMX. For additional information on Central Processing Unit, also see the following articles: Addressing Mode, CISC, Computer Bus, Computer Engineering, CPU Cooling, CPU Core Voltage, CPU Design, CPU Power Dissipation, Floating Point Unit, Instruction Pipeline, Instruction Set, Notable CPU Architectures, RISC, Wait State. The sound file and all text in this article are licensed under the GNU Free Documentation License, available at http://www.gnu.org/copyleft/fdl.html.